of materials? Heard about anyone? No one? What are that elemental analysis is there? If you want to do elemental analysis of one, let's say one steel or one alloy, so what characterization you will do? Anyone? Anyone? No one? Ken? Kausal?
Yes, sir, I'm not sure, sir.
Lohit? Yeah. Please tell, Pooja.
X-ray photoelectron spectroscopy.
Yeah, but that is actually, do you know any other like actually elemental analysis method? Any other, like you heard about EDS along with ACM can be done?
Yes, sir.
So this is actually this EDS as well as XPS. These are actually elemental analysis, and XPS little bit high-end elemental analysis. So that is actually often used in material science to analyze this, like what are the information we can get, like we can get what are the element present, we can get what are that actually bond formation, let's say the oxides. So what are the bond formation is there? If you some defect is there, so we can quantify that how much amount of point defects are there. That is we can quantify. Let's say that one atom is means metal ion is atom is in two different state, metal ion. So which state in how much percentage? That is also we can calculate. Let's say that Fe +2 as well as +3 is there. So we can calculate. So that is actually very powerful and very useful method. So there actually high vacuum is required. Yeah. So you are getting my voice now is clear?
Yes, sir.
Yes,
Okay.
yes, sir.
So now actually let's move very fast because today already is little bit delayed. So why is vacuum needed? So you can see this is one normal chamber. Then when you do the vacuum, what happened that air molecule means oxygen as well as nitrogen and sometimes H2 also, this number will reduce. So and what will, as a result, what will happen? Let's say that you are depositing gold. So gold atom in vapor state, it can actually move without any hindrance. So to move a particle in a straight line over a large distance. So that is the main purpose of this vacuum. But along with this, some other purpose is also there. So that is actually I'm going to talk. So like in atmosphere, like if we do a like deposition, so what will happen that contamination usually water. Okay, so what will happen? Just I'll give one example. Like when I was a student in IIT Kanpur, so I mean one day actually I deposited one in physical paper deposition unit one small molecule that is called pentacene, that is actually by physical paper deposition, and that is organic semiconductor. Then I made it one transistor, that thin film transistor. Then I found that it didn't work. Then I didn't found that what is the problem, that it didn't work. Then I realized that I did deposition actually in 10 to the power minus 5 millibar vacuum. But ideally actually it should be deposited in 10 to the minus 6 millibar vacuum. So what happened that in 10 to the minus 5 millibar vacuum, there is a contamination of water is more. And particular, this semiconductor, if you deposit, is very much actually it's sensitive to this contamination. And immediately, I mean, then actually I found that my device actually is not working. So that's why actually this contamination is a major problem in electronic application. So that's why in high vacuum, if you do it, so that this kind of actually moisture will be less in the atmosphere, and this moisture will be a natural tendency to absorb on the surface. So when it will be absorbed on the surface, what will happen? Then on top of this water molecule that your like semiconductor atom or maybe metallic atom that will be deposited. So it will remain trapped as a contamination there itself as impurity, and that's why actually ultimately it will degrade the device performance. But if you do in high vacuum, that you can get a clean surface because this moisture level will be very low, and then of course that actually contamination will be less. Now, why do we need a vacuum? So to keep surface free of contaminant, and this process film with low density of impurity. So ultimately that actually there are actually two kind of, here one thing is that adsorb moisture may surface on the surface and could be trapped, so that contamination. So that is, and also that during the deposition also this molecule may come, this contaminant molecule, and it will may trapped. Okay, so the process film with low density of impurity. So that is actually, if you have a good quality vacuum, high vacuum, then process film will be low density of impurity. And in case of actually, this is in case of sputtering, maybe after 2 class I'll start the sputtering, then I'll talk about this, maintain this plasma discharge for sputtering source. That is actually for the time being you just keep it, and this large mean free path of electron and molecule. So mean free path of electron will be large. So mean free path means that distance between traveling distance between two successive collision, and that mean free path for air at 20 degrees Celsius. So at room temperature we can say that lambda equal to 68 nanometer. So this is the mean free path for air, 68 nanometer at room temperature. So that it means you can see that 68 nanometer. So that means if I want to deposit at room temperature, what will happen? That atom actually will very difficult. It will not able to go that whatever that maybe I melt it, and then some gold atom that is actually will make a lot of collision with this air molecule. So that means vacuum chamber is compulsory in physical vapor deposition. Okay, so vacuum. So what is the purpose of the vacuum? Mean free path will be very high. So this source material without any hindrance it can reach to the substrate. And second, if we have a vacuum, the substrate contamination will be less. As a result, that final film will be high pure. So now pressure, one standard atmosphere, that is 76 torr or 1013 millibar. So that is already at sea level at 0 degrees Celsius. So that is actually, we called it one standard atmosphere. Now this pressure equivalent, like actually as I told that like gauge pressure, this atmospheric, this is actually atmospheric pressure equivalent. So if gauge pressure PSIG is 0 pound per square inch, PSIA 14.7 inch of mercury, 76, then millimeter of mercury, that is 76, that is from our school days we know. And this unit also in European countries, some of the countries still use this kind of unit. So that's why I told that it depends on the company to company, whatever company material you are, this pump you are purchasing and whatever gauge. So gauge actually is purchasing. So gauge will show the reading of this vacuum inside the chamber. Then 76 torr, then this 76, then 40, that millitorr, and then this one actually Pascal, then 1.013 bar or 1013 millibar. But you have to remember only that if you want to deposit the torr, millibar, these two things actually if you remember, that is actually more than sufficient. So one atmosphere means 760 millibar. Okay, so sorry, 760 torr or around 1000 that millibar. Okay, means 10 to the power 3 millibar. So that is actually you have to keep in your mind. And 760 and this is 1000, almost both will be near about that 10 to the power 3 order. And sometimes actually this Pascal also sometimes is being used. So in case of Pascal, then it will be around actually 1 to 10 to the power 5. So this is actually here also that same thing. So these things is important. So 10 to the power 5 Pascal. So 1 atmosphere, 10 to the power 5 Pascal, 10 to the power 3 millibar, 760 torr. So these things you have to remember. This one you have to remember. Then actually absolutely no problem in any chamber. You can understand that what is the vacuum level compared to atmosphere. And in India, the most of that instrument will be in atmosphere, Pascal, millibar, or torr. That have four things are used. Atmosphere is rarely used. That Pascal, millibar, and torr. So now this range of the vacuum. So rough or low vacuum, that is actually 760, 759 to 1 into 10 to the minus 3 millibar. So that is actually you can achieve. Then high vacuum. So this low rough vacuum you can achieve by some low cost pump called actually roughing pump. And then actually high vacuum 1 to 10 to the minus 3 to 1 into 10 to the minus 8 millibar. So that is actually generally in this zone that your physical vapor deposition is being done. Okay. So if you not maintain, then actually it will be contaminated. So this part actually very important in physical vapor deposition. And if you think for the electronic application, so that's why actually I visited that in Seoul, this Samsung, they are actually R&D lab. So there are around 2,000 scientists is working for, they are actually very big display lab. So they actually use that totally that, some protected rooms are there to avoid the contamination. So if you want to enter there itself in that chamber, in that fabrication unit, so you should have proper dress, proper shoes, then actually mask, then gloves, hair net cover, so shoe cover, everything. So then only actually you will be allowed to, and they have a actually standard clean room. So we, how many heard about clean room? Anyone heard about clean room? So clean room actually is actually where that fabrication or micro fabrication or biological study like cell culture, this kind of study is being done. So in clean room actually particle per unit volume actually is measured. So how many particles are there? So that particle actually you will be very less if you are very sensitive, like in pharmaceutical company or in microelectronics company where the fabrication is going on. So there actually this clean room particle number of particle will be very less per unit volume. Okay, so this is actually the different and ultra high vacuum range. So less than 10 to the minus 8. So that is also sometimes is required, like actually XPS, UPS. These are actually high end analysis. So X-ray photoemission spectroscopy, then ultraviolet photoemission spectroscopy. So this kind of study actually we need very ultra high vacuum is required to understand the surface behavior. So molecular density and mean free path. So this is actually the schematic diagram is saying the 50 psi. This is 100 psi. So in 50 psi, you can see the number of molecule is less. So gas molecule collide with one another and lower pressure result in fewer molecule per unit volume. So your target will be their number of molecule should be less in the chamber. And this in the evaporative deposition system that earlier described, a larger mean free path means there actually are fewer molecules of air present to deflect that evaporant metal. So this part is very important. So this fewer molecule of air present to deflect that evaporated metal. So whatever evaporated material or metal is there, so that is actually should not deflect or should not have a collision with the air molecule. Now there are two things. One is called viscous flow and another is molecular flow. So in atmosphere and in at room temperature, so 1 atmosphere and room temperature, they're actually in a closed chamber that you can see that these are so many gas molecules are there, and these gas molecules actually momentum transfer between the molecule during the collision. So when there is a collision, momentum transfer will be there, and this is called the viscous flow. Okay, but like actually whenever that molecules moved independently, we called it molecular flow. So in physical vapor deposition, we want this regime that it should be in molecular flow regime, not in the viscous flow regime. So in molecular flow regime, that actually you can see the mean free path is actually very high. In next slide, I will show you that how the mean free path is actually changing and it became very high. So in viscous flow, what is happening? The distance between the molecules is small and collision between molecules dominate and flow through momentum transfer. Okay, so these are the very important, and generally P is greater than that 0.1 millibar. So 0.1 millibar greater than 0.1 millibar. So in that pressure range, this viscous flow actually will dominate. And now transition flow, that is a region between the viscous and molecular flow. But where is the molecular flow? The distance between the molecule is very large or very large, and collision between molecules and walls. So collision between molecules and walls dominates. So these are very important. So molecule collision is less. Molecule and collision, wall dominates. So it will hit through the wall, but number of molecule is less. So that's why molecule collision is low, and flow through actually random motion, and generally P is smaller than 10 to the power minus 3 millibar. Okay, so that's why actually 10 to the power minus 3 millibar, that below that range you have to reach to get that, I mean, the system, make it get system ready for physical vapor deposition. Now the mean free path. So in mean free path, actually this is 1 atmosphere and molecules per centimeter cube. So 3 into 10 to the power minus 19, 30 million trillion. So 3 into 10 to the power 19, 3 to 10 to the power 19, this number of molecules per centimeter cube at room temperature. Sorry, at 1 atmosphere. If I go to that 1 into 10 to the power minus 3 millibar, then 4 into 10 to the power minus 13. So 6 order of magnitude actually reduced, so 40 trillion. And then if I go to 10 to the power minus 9 millibar, very high, 10 to the minus 9, that very high region, that is actually here, this ultra high. So 10 to the minus 9, here in this region, you reached in this region, ultra high vacuum. So in ultra high vacuum, what is happening? 4 into 10 to the power 7. So again, 6 order you reduce. So that means per centimeter cube, whatever we call very high vacuum, so there also some molecule always will be there. Okay. And now let's have a look the mean free path. So in 1 atmosphere, then at room temperature, they are actually 25 into 10 to the minus 6 inch or 6.4 10 to the minus 5 millimeter. So that is actually mean free path. Okay, that this is actually that it's mean free path is coming like this. Whereas this one, this in 1 into 10 to the minus 3 millibar, that you can see that 5.1. So this is actually 10 to the power, this is millimeter, so in centimeter it will be 10 to the power minus 6. Okay. And this is actually 10 to the power minus 6, and here you can see 5.1 centimeter. But if you reach to high vacuum, you can see 50 kilometer is the mean free path. So 50 kilometer when is the mean free path? Do you think that two atoms will collide? Never. They will always collide with the chamber only. Okay, so mean free path actually became very high. So now another one important terminology is that monolayer time. So what is this monolayer time? So we define the monolayer time as that the time for one atomic layer of gas to adsorb on the surface. So one full atomic layer will form in which time? So that is actually tau equal to 1 by SZA. What is SZA? S is the sticking coefficient. Z is the impingement rate for air, that is actually 3 into 10 to the power 22. And then area of an adsorbed site, so that is also this, if I assume that A equal to 1 angstrom square, so that will be this centimeter. So at 3 into 10 to the power minus 5 torr, it takes about 1 second for a monolayer of gas to absorb on a surface. Assume sticking coefficient is equal to 1. Now, if I go for high vacuum 10 to the minus 9, it takes 1 hour to form monolayer for S equal to 1. Sticking coefficient assume 1. Why 1 hour is taking and here 1 second? Because number of molecules are less. Previous slide already we have seen the number of molecule is less. So that's why it's happening. And for most of the gas at room temperature, S will be very, very less than 1. So monolayer time is much longer. Okay. So monolayer formation time will be even much longer. For the simplicity, we are assuming this case S equal to 1. So that is actually called monolayer time, that actually, so that actually time required to form one monolayer of adsorbed gas on the surface. Okay. So that's all actually, and if you have any questions, I shall be happy to answer your question. Any question? Please do ask.
So SZA, can you explain it again? SZA.
Okay.
SZA.
So this is actually very simple. Like they say that green color is that substrate. So on the substrate, one full layer, like this here, 3 atoms are there. Like actually, if I put it in between one atom, here also one atom, and entire surface should be covered. So that is actually we call whatever time required to cover the entire surface. Okay, so that is we call one atomic layer of gas. So one monolayer formation. So we define the monolayer time as time for one atomic layer. Atomic layer means that thickness of this layer equal to one atomic diameter. So one atomic layer or near about one atomic diameter of gas to adsorb on the surface, that is tau equal to 1 by SZA. So S is here sticking coefficient. So S is actually adsorb. This is actually sticking, whatever that sticking coefficient. What is the sticking? That coefficient, that is, for simplicity, we are assuming 1. And then impingement rate for air. So whatever that its impingement on, because if you vacuum, along with the vacuum, that impingement rate will different. And in this case, actually, we assume that temperature is fixed at room temperature, let's say. So impingement, whatever the gas atom will hit, so that atom will actually hit on the surface, it can hit on substrate also. So that is random heating, and that during heating it may absorb. So that monolayer, so that is actually impingement rate and area. Whatever that area, that adsorption of an adsorption site. So that is the 3 terminology. And 3 into 10 to the minus 5 torr, number of atoms, molecule will be less. So monolayer formation and sticking coefficient, if we assume S equal to 1, then 1 second is required for one monolayer formation. But when 10 to the minus 9 torr, it takes 1 hour to form one monolayer formation. Okay, so that's the difference. Any other questions? Any other questions? So if no more questions, then just I'll take the attendance. And this part is very easy. So, and this slide as well as this inbuilt audio, actually I'll put it there. Yeah. Okay, so there is no more questions. So just let's wrap up here itself. Thank you.